Hi, my name is Jeffrey Shen, and I am a senior in the Math Science Technology program at Paul Laurence Dunbar High School. Today, I'll be presenting to you my capstone research project on improving the trainability of generative adversarial networks, where I worked under the mentorship of Dr. Brent Harrison at the Department of Computer Science at the University of Kentucky. So for an overview of my presentation, I'll first cover the background information related to my project. I'll then go over my engineering goals. I'll go over my methodology and my results for the project. I'll then talk about my conclusions and further research. I'll give my acknowledgements, and I'll show my references. Finally, I'll open the floor to questions. So to begin, I'll first talk about what machine learning is. At its core, machine learning is a subset of AI that uses an algorithmic approach to solving problems and identifying patterns. In machine learning, a mathematical model is built, and the trainable parameters within the model are iteratively updated based on the given training data to solve the given problem. Deep learning is a specific subset of machine learning, which uses a neural network or multi-layer perceptrons as the model architecture. There's many applications of these deep machine learning models, including image recognition, natural language processing, and bioinformatics. For generative adversarial networks, or GANS for short, are a type of deep learning model which generates new instances of data based on the training data. For example, if you give a GAN a dataset of images of cats, the model should theoretically be able to learn and produce entirely new realistic images of cats. A GAN is actually composed of two neural networks, a generator and a discriminator. The role of the generator is to generate new instances of data, while the role of the discriminator is to identify which of the input data is real or generated. You can imagine a GAN as analogous to a cops and counterfeiters scenario, where the generator is the counterfeiters trying to pass fake money, and the discriminator is the cop trying to identify which of the money is fake. This competition inherently drives self-improvement until the generator is able to generate realistic data. The most prominent uses of these GANs currently is through image synthesis. This slide shows a visualization of the GAN architecture using images of handwritten digits as the training set. Specifically, the generator network takes in a latent or random noise vector and maps it to a fake image, while the discriminator takes in both real and fake images and tries to map it to a correct label, real or fake. The goal of the discriminator is to become better at detecting whether images is real or fake, while the goal of the generator is to try to generate images which can fool the discriminator. In other words, the discriminator is trying to maximize its own accuracy at classifying images, while the generator is trying to minimize the discriminator's classification accuracy on its own generated images. While GANs are capable of creating incredibly realistic images, there are some important limitations to these GANs. Firstly, they are notoriously unstable during training. The training process requires a balance between a generator and discriminator. If one of them overpowers the other, the training process is stalled. Secondly, they require a large amount of training data to train, which can be difficult to obtain. Lastly, because of this, they are computationally expensive to train, requiring a large amount of computational resources and time. This is where transfer learning comes into play. Transfer learning is a specific technique in which a machine learning model uses knowledge gained from solving one problem and transferring it over to solving a different problem. Therefore, the model does not have to start learning from scratch, and instead only has to adapt its knowledge to solve a similar problem. For this project, I'll be using a pre-trained image classifier as a discriminator. These are models that have already been trained extensively to accurately classify images. However, these models can also act as feature extractors for images, in which they compress an image into a smaller representation of data, in which only the most important parts of the image are retained. Then, by comparing the L2 distance between the features from a batch of generated images and a batch of real images, we can create a loss function for the generator to minimize. In other words, the objective function of the generator is to minimize the distance between the features of the real images and the fake images. This technique differs from typical GAN training process in that the generator learns from the model already trained on image detecting, instead of a model that is randomly initiated. With this technique, the generator training process is not constrained by the limitations of the discriminator, but instead by a model already extensively trained on detecting higher level features and patterns within images. This technique is both more stable and more cost efficient, since only one model is being updated during each training iteration, the generator. This brings me to my engineering objective, which is to improve the trainability of GANs using this transfer learning technique. So for my methodology, the dataset I use is called the Oxford 102 Flowers dataset, which is a collection of about 2,000 images of flowers found around Europe. I chose this dataset because the amount of data in it is small, which will make it difficult for a normal GAN to train on. I built two GAN models, one using the standard technique and one using the transfer learning technique in the Python programming language. The model architecture and optimizer was taken from a model architecture described in a previous paper titled Unsupervised Representation Learning with Deep Convolutional GANs, which was shown to be effective in training GANs. For the transfer learning GAN, I used a pre-trained ResNet model with the last layer stripped to become a feature extractor. I use PyTorch, which is an open source machine learning library, which gives me the tools to build and train a machine learning model. I trained for about 600 epochs on Google Colab, which is a free cloud service that supplies a free TPU for me to train my models on. Finally, I evaluated my results using the Frechet Inception Distance Score, which is a metric used to evaluate the performance of GANs. I'll first show my quantitative results, which is shown here. And to note, a lower FID score corresponds to a shorter or smaller distance between the real and generated images, and thus more realistic images. As you can see, the GANs trained with the transfer learning technique actually performed worse than the control GAN, although both of these GANs were still far from achieving a realistic scores from the baseline images. This slide shows some example of synthesized images from each GAN. On the left is a batch of images from the dataset. The middle is a batch of generated images from the GAN trained traditionally, and on the right is a batch of images trained with the transfer learning technique. As you can see, the middle batch, the GAN in the middle batch is able to learn the overall shape and color of the images in the dataset. However, they're missing finer details, which pushes the images over to realism. And the GAN trained on the transfer learning technique, you can see there are noticeable artifacts on image which severely degrade the quality of it. In conclusion, the transfer learning technique did not improve the performance of GANs. Although the training process was faster and more stable, it resulted in worse quality images being synthesized, and neither of the models were able to create realistic images. Importantly, I didn't find any evidence of overfitting or memorizing training data on either of the models. However, there are some limitations of this project that I would like to explore further. In this project, only the generator was trained, and the lack of trainable parameters in the feature extractor means that it was only limited to the knowledge gained from the dataset it was trained on, which could be wildly different from this dataset. By adding trainable parameters to the model may be able to learn to adapt to the target domain. And in the future, I would like to explore to see if adding these trainable parameters onto the feature extractor can improve the performance of an overall GAN. I'd like to thank Dr. Brent Harrison for being my mentor, and the University of Kentucky and the Kentucky Young Researchers Program for allowing me to work on this project. I would like to thank the Math, Science, and Technology Center for also giving me the opportunity to work on this project. And I would like to thank my family and friends for supporting me along the way. These are my sources. And that concludes my presentation. If you have any questions, feel free to email me at my student email, jeffrey.shen@stu.kyschools.us. Thank you for watching.